All right, from the unit conversions and stuff? Yeah. I'm sorry. Next time I should bring the problems. Okay, so it was a number. So the question is something like this: how do you write 4 point something in scientific notation, right? Just leave it like that. But that's already in scientific notation. I mean, you could write it times 10 to the 0, but don't do that. That's stupid. If you did that, I'm not saying you're stupid. Yes. Sure. Okay. This is number 9. Okay, so, well, this one, just to get it in the notes, let's just say that already is. Just leave it like that. If on a test, if you do write it as 4.7 whatever times 10 to the 0, that's, you'll get full credit for that. If you leave it like this, you'll get full credit for that. So number 9 on units. Oh yeah. Oh, okay. So number 9 is for after this class. But let's do one like that. I'll do number 9 for you. You have enough on your plate. Let me help you. So 15.5 kilometers it starts with. And let's convert it to millimeters. Well, here's what we know. Kilo equals times 10 to the 3rd. And milli equals times 10 to the minus 3rd. And so 15.5 kilometers, I'm just going to rewrite that as 15.5, replace the kilo with times 10 to the 3rd, and that's meters. And so that's the starting point, and now we're just going to convert meters to millimeters. Well, another way of writing this is that 1 meter is equal to 1 times 10 to the minus 3rd. No, that is not right. 1 millimeter is equal to 1 times 10 to the minus 3rd meters. So 15.5 times 10 to the 3rd meters. We want to cancel the meters, so I'll put the times 10 to the minus 3rd in the denominator. And millimeters go up there. You can see the units cancel. So now we're in millimeters, and we just have to multiply this out. We get 15.5 times 10 to the 3rd divided by 10 to the negative 3rd, which is multiplying by another 10 to the 3rd. So this is 15.5 times 10 to the 6th millimeters. And then in scientific notation, think of breaking this scientific, it's in sort of scientific notation, but it has more than one leading digit. We need to fix that if we're going to put it in scientific notation. So I'm going to multiply or divide this by some multiple of 10 to get one leading digit. And then I'm going to do the opposite to this one to keep it the same number. Okay, so 15.5. Do I have to multiply by 10 or 100 or 1,000 or divide by 10 or 100 or 1,000 to get one leading digit? And divide that by 10. And then what I do to this is determined by what I did to this. If I'm dividing this by 10, in order to keep the same number, I have to multiply this by 10. So this is going to be 1.55 times 10 to the 7th. Any questions about that one? Any other homework questions? All right. Well, so that was just an introduction to units and unit conversions. Now we're kind of getting into the first physics topic in a way. So the first thing that we're going to work on is kinematics of a particle in 1D. So there's a lot of information in that title, and you haven't heard a lot of these things before, so I'm going to just carefully define kinematics, carefully define particle, carefully define 1D. Okay. So kinematics. Kinematics is the part of physics where all you're doing is describing motion. You're describing motion without including any of the causes of the motion. You don't deal with the masses of objects. You don't deal with forces applied to objects. You're just talking about relationships between position, time, velocity, and acceleration. And today we're going to start getting into defining those. Another way to think of this is you can get kinematics information completely from a careful video. You can see where objects are at a given instant. You can measure how long it takes from an object to get here to here. You can use that to calculate how fast it's going. But a video doesn't give you any information about the object's mass, about how hard things are pushing on it, stuff like that. So what you can get from video only, Okay, and then this is the part that we're dealing with now, but it's making a distinction between kinematics and the next thing that comes on where we include the causes. And I have no idea why anyone would have done this, but maybe it goes back to Latin or something. Kinematics is, we're distinguishing between kinematics and the next thing, which is called an almost identical thing, kinetics. And I remember those being hard to keep straight in your head because they're so similar. So kinetics combines kinematics with causes of the motion. And by the causes, I mean mass and force. It's a horrible nuisance that those sound so much the same. This is the way I remember it. Although I have to say with Jerry here, I'm embarrassed to say this. I don't mean anything by this to anybody. This is just how I remember it. But which one of those two is simpler, kinematics or kinetics? Kinematics is like the easier one. So I always think it's so simple your ma could understand it. Okay, that's how I remembered it. I'm sure you all have very smart moms, but I don't mean anything by it. Okay, so this is the one that we're doing, kinematics, right now. And the next thing we have to define is a particle. When you think of what a particle is, you probably just think of something small. And there is a connection between small things and treating them like particles. If you're mathematically, if you're treating an object like a particle, so an object that you treat like a particle mathematically is an object that's treated as having no length dimensions. So it's the size of a point. No size at all. And if something doesn't have any size, you can't make any distinctions between different parts of it. Everything's happening at the same location. So you can't make a distinction between the left and the right or the top and the bottom. It's all the same. Okay? And so because you're treating things as having no size, there's no way to discuss the orientation of an object you're treating as a particle. So there's no, I'll just say no orientation. Because you can't tell what part of it is aiming this way or that way. It's all at the same point. So the next question is what? So we're always in physics trying to make a connection between a mathematical treatment like this and a real physical thing in the world. So what kind of real physical things in the world are particles? And the answer is, so most likely your first thought is, well, the small things in the world are particles and the big things are not. And there's some truth to that, but of course, everything, almost everything except the smallest subatomic particles there are small compared to, big compared to something else. So like, at what point do you say like, okay, well, is a baseball a particle? No, because there's stuff a lot smaller than a baseball, and baseballs spin and whatever. So what's small enough to treat as a particle? So it really doesn't come down to the size of the object. It just comes down to what information you care about in your treatment of the object. So what physical objects can be treated as particles? And the answer is really anything. Anytime you don't care about something's orientation, you only care about tracking its center of mass, you can treat it as a particle no matter how big it is. So any object where you care about the center of mass location but not its orientation. Like one example of something that's gigantic that you treat as, people often treat as a particle, is a planet or even a star when people are doing calculations that have to do with planetary motion. Since people are usually just concerned about where a planet is in its path, and they don't care about which direction this part of it is facing or anything, because they're only concerned about its gravitational pull, people tend to treat planets as particles, so they just treat it as if it's only a dot with a certain mass that's at the location of its center. And obviously a planet is huge, but if you don't care about the orientation, it's usually a fine treatment. And then there would be other applications where you might want to know the orientation of a planet. You want to know when you can see the spot on Jupiter or something, or for example, we'll do a lot of calculations where we treat a car as a particle because we're trying to do calculations about where the location of it is. But in other applications, if you're like an engineer or whatever, it's very important to you that when the car finishes doing whatever it's doing, it's on its wheels instead of on its top, And in that sense, like, orientation is really important. So it depends what you're using the calculation for is the answer. Why didn't I just say that at first? And then the last thing is one-dimensional, 1D. An object is in 1D motion if it's moving along a known path. And so if something's on a given path, at any instant it only has two choices of a direction it can go. So at any point, it can only move forward or back. So there's only two directions in a one-dimensional world. And that makes things easy in one dimension because we can use the sign of a number, whether it's positive or negative, to tell us its direction. So any object, any quantity that has direction associated with it, we can use positives and negatives to give us that direction. And that's exactly because there's two two signs, positive and negative, and those correspond to the two directions that exist in a one-dimensional world. So positive and negative to indicate direction. That's not true in 2 dimensions or 3 dimensions. So let's think about something in 2D. So say that this particle can move in 2 dimensions. That means it can move in all of these directions. It has infinitely many choices, no matter where it is of where it can go. And so having just a plus and a minus isn't enough anymore to specify what direction it's going. So there's infinitely many directions. And so plus and minus aren't enough. And we'll have to introduce this new way of talking about directions when we get to 2D. And that's called vectors. So the nice thing about one dimension is we don't have to deal with these complicated math things called vectors. We only have to deal with plus and minus. And that'll let us introduce some of these ideas of physics before the math gets complicated by this new mathematical thing, vectors. Okay. Any questions so far about those 3 definitions? We have our first quiz on Thursday at the end of class, remember? And this is an example of the kind of thing that I'm likely to ask questions about, you know. Give me a definition of 1D. Give me a definition of kinematics, that kind of thing. Okay. So these are the parts of your notes that you should pay extra attention to when you're getting ready for the quiz. Okay, so we're going to talk about, so the quantities that we're going to use mainly have directions associated with them. And the ones that are going to be important for us are position, displacement, velocity, and acceleration. We don't tend to use these directional quantities in everyday speech. We tend to use similar things that don't have direction associated with them. So I want to first make just a little table that shows all these directional quantities that we're going to be using and the kind of corresponding everyday non-directional quantities that you're used to. So over here will be the directional quantities. Over here is the non-directional equivalents. So the first one that I'm going to define is position. That one we don't really, in everyday speech, have an equivalent of position. You just sort of describe where you are compared to the stop sign or whatever. I'll leave that one blank. And then we're going to use position to define one called displacement. And rather than talk about displacement, we usually talk about distance. So those are related, but not the same. The third directional quantity is velocity. And the equivalent to velocity, if you throw out the directional information contained in velocity, is speed. And then the last one is maybe the most confusing one. The directional quantity is acceleration. The non-directional one that we use in everyday speech, we also call acceleration, but it sort of means something different. So we talk about acceleration and deceleration, talking about whether something's speeding up or slowing down. Acceleration to us is going to have a different, related but different meaning. Okay, so I'm going to start by defining position. And everything that we're going to do in kinematics so everything in kinematics is based on defining a numeric value for position a numeric value for time so let's say the numeric value for time I'm going to call lowercase t, and the numeric value for position I'm going to call lowercase p. And then once we have those two things defined, we want to write position as a mathematical function of time. So position is a function of time. So what I mean by that is, like, for example, you could have a function p of time that's equal to 5t squared. For all time greater than 0. Okay. And, you know, you've seen functions like that before. The idea here is that with this function, we have an infinite number of coordinates where we have a time and a corresponding location of the object we're tracking. Yep. Yep. That's nice. I have a bad habit when, like, I look out and, like, everyone's, like, silent and looks, like, nervous or whatever. I'm like, oh, they hate this, and then I'm like, I'll rush through it so we'll get to something they like. But that's like the opposite of what I should do, because it's usually stuff that's complicated. But if we know that the position is equal to 5t squared, when time is equal to 0, what's the position? Yep. So 0 squared times 5 is equal to 0. When time is equal to 1, what's the position? Yeah, so 1 squared times 5 is 5. And then these would all have units associated with them. So like let's say this is in seconds and meters. So at 1 second, the position is 5 meters. and so on. Okay, so that's what we're trying to do. That's where we're trying to get to, is to come up with a way to define a number for time, a way to define a number for position, and then a way to represent position as a function of time, so you can do math with it. So how do we assign a number to position? Let's say that, okay, so these are train tracks, and this is a train. This is the only kind of train I know how to draw. Okay, so the train's heading down the tracks. First of all, is this one-dimensional motion? Yes. So a lot of times people think of one-dimensional motion as being on a line, but it doesn't really have to be on a line. It just has to be that at every point. That's what we have here. So how do we assign a number to, we want to have a single number that defines the location of that train. In order to do that, you first have to arbitrarily pick two things. So you must arbitrarily pick a zero position and second, a positive direction. Once you make those two choices, you can use those to tell you the location of the thing that you're tracking. So let's say that we're doing this in meters. Okay, so we already have like distances defined, and let's say that we pick this point here. Maybe there's some like landmark there or something, and we call that our zero. So our zero position, I'm going to write with a scripty O, like origin. And then let's say our positive direction is along the tracks this way. That means, so if this direction is positive, that means that direction is negative. And now that we've defined the zero position and the positive direction, we can measure using a meter stick where the train is in comparison to that zero. I'm going to do one more thing. Since we're treating the train as a particle, we have to choose a point on the train that represents its location. And usually the best choice is the center of mass. So this symbol here that's the center of mass symbol. So that point there represents the location. Like in like car commercials when they have the crash test dummies and they have these symbols all over. Did you know that's what that was? Shoot, I was hoping to surprise you. But the reason that the crash test dummies have, so like a crash test dummy has a center of mass thing here and here, like every solid part of the crash test dummy has these center of mass things on it. And that's because the center of mass is a really important location in physics. And so if they, in a video, they watch a high-speed video of this collision, and they see what happens to the center of mass of each one of these body parts, they can use that location and go back and do physics of, what the forces are on the different joints and stuff. So that's why they do that, by the way. Okay, so we have that zero position in the positive direction. Now I'm going to count back meters. I'm going to measure how far it is from the zero to the to the center of mass of the train. So let's say that's 1, 2, 3, 4. I don't know, that's a small train. So we know that along this path, it's 4 meters from the 0 to here. Okay, and to get from the 0 to the center of mass of the train, you have to go in the positive direction or the negative direction. Positive would be counting this way. So we're always starting at the 0. Okay, so we're going in the negative direction, 1, 2, 3, 4. So if you go 4 meters in the negative direction, what's the number at that location? Yep, so this is -4. Yes. So then you can assign a numeric position to every location. Since you can't assign a numeric position to a location until you make those choices, if there's any problem you're given where they give you a position as a number, like, for example, this one I did here, where I already gave you the position as a function of time, that means those choices have already been made for you. Okay? There's no way to assign a number to a position until you make those choices. And this is a mathematical idea, but it's also, it's the same way that we talk about locations in everyday speech. We don't do it numerically all the time, but if somebody asks you, you know, where the restaurant is that you're meeting at, you pick a reference location. You say, like, okay, you know where Calhoun Square is? They say, yeah. And then you say, okay, it's about 3 blocks east of there on Lake Street. You know, so what you're doing is you're giving a reference, like our 0 position, and then you're telling them which direction to go and how far to get to that location. And that's exactly what we're doing with this number scheme. So once you assign a number to a position, you can represent that position on a number line. So in this case, there's the number line. There's the 0, 1, 2, 3, 4, 1, 2, 3, 4. Here's -4, and this is the location of the train at that instant. Okay, so I said that what we want to do is we want to come up with a relationship between a numeric position and a numeric time. But we don't have yet, we don't yet have a way to represent an instant in time with a number. Now we have a way to represent a position, but you know, what time did the train get to that spot? Like 1,000, you know, it doesn't have any meaning yet. But if you, okay, so let's say now what we want to do is assign a numeric time to an instant. In order to do that, you have to choose an instant that you're going to call your 0 time. You can think of that as like the instant you turn your stopwatch on. Then the numbers that you read on the stopwatch as times go by is the time of each one of those instants. With time, you don't have to choose a forward direction, a positive direction, because time only moves in one direction. But it's sort of the same idea as the reference for position. We're choosing this reference time to compare stuff to. So now, if we had chosen, if we had said our 0 time is going to be 8 seconds before this picture was taken here. So, for example, let's say time equals 0, 8 seconds before the train picture above. Then the instant of the picture has the numeric time 8 seconds. And that means that you can plot the position and the time of that train on a position versus time graph at that instant. So you can now plot it on a position versus time graph. So in a position versus time graph, we're always going to have, so these are the axes. The x-axis is always going to be time. The y-axis is always going to be position. And for this example, time is given in units of seconds. Position is given in units of meters. And if I count out the seconds, there's 1, 2, 3, 4, 5, 6, 7, 8. And the location, -1, 2, 3, 4. So there's -4. Here's 8. This spot right here indicates the time and location of the train. Any questions about that yet? And the idea is, what we would really like is we'd like to know the position of the train as time varies. So we'd like to, this is the picture that's drawn above, but maybe we'd like to, know something like that. That's what happens over time as the train moves. One thing, this is important. There's no mathematical reason that you couldn't talk about negative times. The math would all work, but nobody does, and so we're not going to. So in this class, we'll never use negative time. Okay. Now I'm going to define displacement and distance. So let's say that we choose two instants. Two instants, I'll call them T1, T2. T1 is the earlier instant and T2 is the later instant. And the displacement from T1 to T2 is, I'll call it lowercase d, and it's the position at instant T2 minus the position at instant T1. So let's do an example. So let's say that this is the position versus time graph of, let's say this is the position versus time graph of the object we're tracking. So 1, 2, 3 seconds, and 1, 2 meters, and then we'll go down to -1 meter. And let's say that when time is equal to 0, the object is at position +1. So the horizontal is the time. So our coordinate 0, 1 is right here. That's time is 0, position equals 1. And then at time 2 seconds, at time 1 second, we're at position 2 seconds. So on this graph, that's there. Please ask questions if you're confused about what I'm doing here. If you can, sometimes wording a question is the hardest thing, but if you can think of a way to clarify something, please do, because I'm sure other people are having the same issues or similar issues. And then at time equals 2 seconds, the object is at -1 meter. And then finally at 3 seconds, the object is at 0 meters. And I'll just fill all these in. So the path looks like that. And say we want to calculate what's the object's displacement from time equals 0 to time equals 3 seconds. And then second, what's the object's displacement from time equals 0 to time equals 1 second. Okay, so for part A, The displacement is going to be the position at the later instant, 3 seconds, minus the position at the earlier instant, 0 seconds. Looking at this graph, what's the position at 3 seconds? 0? Yep. So 0, and then minus, what's the position at 0 seconds? 1. So we get -1 meter. And then for part B, the displacement, we want just from 0 to 1 seconds. So the displacement is going to be the position at 1 second minus the position at 0 seconds. What's the position at 1 second? +2. What's the position at 0 seconds? 1. And so the displacement is +1 meter.
Meters, like just your work, or just in the final?
Oh, that's a good question. I think for so far, I'm not worried about that. But we are pretty soon. We're going to start doing calculations where I am going to want you to carry the units through. But in my examples, I'll do it that way too. Okay, so what does it mean that one of those is negative and one of those is positive? That's an important idea here. Displacement from the displacement from 0 seconds to 3 seconds was negative, and from 0 to 1 seconds was positive. Well, that's that directional thing, and what that says is that the net motion, it went through all this motion. But the net motion was just going from +1 to 0, and so the object that we're tracking overall moved in the negative direction. Okay? So that negative sign tells you the direction. Since if this was that train we were tracking, we would know the net effect of the train was to move back this way towards what we defined as our negative direction. Okay? So that negative is there's a lot of information in that sign. And then from 0 seconds to 1 second, we went from 1 to 2, so the net motion was in the positive direction. And so for that train, it meant that the net motion of the train would be to the whatever that is, right? So, any questions about that? So now let's think about distance. Distance is actually based on this kind of information. This sort of information is really, we're thinking about it this way because it's designed for this directional information. And so in a way, it's not surprising that it's going to be complicated to come up with distance to throw away this directional information that's built into it. But so now let's talk about distance. Distance doesn't have direction associated with it. So in some way, we're going to have to throw away any directional information that we have. I think the easiest way to do it is to show the path of the motion on a number line. and then break up the whole path into legs, where sort of like legs of the journey, where the object's only moving in a single direction. And then finally just add up the lengths of the legs. Okay, so for example, let's say we want to know what's the total distance traveled from time equals 0 to time equals 3 seconds on the graph shown above. Okay, so here's a number line. Here's the 0 position. Here's +1, +2, and here's -1. The object starts out at position 1. That's at time equals 0. Then the object gets to position 2 at time equals 1 second. The object then travels to position -1 at time equals 2 seconds. And then finally the object ends up at position 0, 3 seconds. Okay, so we're going to break this up into legs of the journey where everything's moving in the same direction. So here's one leg going this way, and the second leg is from here to here, and then the third leg is this. Okay. And we just need to come up with the lengths of those legs. So how long is this? 1. How long is this? +3. And we are gonna add them together, but so the distance is first 1 to get from the 0 to 1 second, then 3 to get from the 1 second to the 2 seconds, and then 1 again to get from the 2 seconds to the 3 seconds. And so you have a total distance of 5 meters. Any questions about that? Okay. I just measured the length from here to here. So that's 1, 2, 3 between those two. That's right. With distance, you throw away all the negatives. You only care about how long that is. Any other questions? Okay. So let's do an example problem that sort of uses all these kind of ideas. Let me say one thing first. So units. This is for position, displacement, and distance. They all have the same units. They all have units of length, so you can use feet or inches or miles. And the SI units are meters. Okay, so here's an example. So let's say so here's the mailbox. Yes, awesome mailbox. And here's, oh, I guess the door will be over here. The door to the house. And here's the car. It's a huge mailbox compared to the car. Yeah. And let's say that this distance is 3 meters. And let's say that this distance, so the distance from the mailbox to the car is 3 meters. From the mailbox, no, from the door to the mailbox is 3 meters. From the mailbox to the car is 8 meters. And let's say that a man starts at the mailbox, walks to the car in 5 seconds, walks back to the mailbox in 10 seconds because he's getting tired, and then walks from the mailbox into the house in 2 more seconds. And here's what we want to do. We want to plot a position versus time graph of this path. And we want to do it where the 0 position is at the car. The positive direction is towards the house. And 0 time is when the man starts walking. Okay, so the way I'm going to do this is I'm going to start out by just showing the motion like on a number line. But before I put any numbers on it, I'm gonna put the physical things. Okay, so there's a car here. There's a mailbox here. And there's a house here. And we know these distances. This is 8 meters. This is 3 meters. And also, before we use the zero position in the positive direction, we know what path the person follows. That's already been given. He starts at the mailbox, then goes to the car, back to the mailbox, back to the house. So the person starts here and travels to the car. And then he goes back to the mailbox and then back to the house. And we know that this leg of the journey takes 5 seconds. This leg takes 8 seconds. And this one takes, what did I say, 2 more? Well, I just put the 8 to go from the car back to the mailbox, and then 2 more. Yes, so altogether that would be 10. Oh, it's 10. Oh, thanks. Okay, so like that. And now we're going to, we haven't used it yet. So far, this is just sort of like a shorthand way of drawing what the man did. But now we're going to use the zero position and the positive direction and the zero time. So the zero position is the car, okay? So whenever the person is at the car, the numeric position is 0. And if, what did we say the positive direction is? Positive direction is back towards the house. So if we know that the 0 is at the car, and that the mailbox is 8 meters in the positive direction, what's the numeric value at the mailbox? Positive 8. And if the house is 3 more meters in the positive direction, what's the numeric value at the house? 11, yep. Positive 11. So what we know so far, we haven't dealt with the 0 time yet, but we know that the man starts at position 8. You see that? And then he goes to position 0, and then he goes back to position 8, and then he goes to position 11. Anybody have any questions about that? And now we have to deal with the 0 time. So the 0 time is when he starts walking. That means that right at this instant, we're at 0. To go from the mailbox to the car takes 5. So 5 seconds later than 0, what's the time at the car? Yep, that's 5. Then 10 seconds later than the time 5 seconds, we're back at the mailbox. What's the time there? Yep, 15. And then 2 more seconds, we're at the house. So what's the final time there? 17. And now we can just read all these values off of the off of that drawing to do a position versus time graph. The positions that are going to matter, the only ones that we have to deal with are 0, +8, and +11. So I'll draw, here's 0. Here's 8. Here's 11. And the times we have to deal with are 5, 15, and 17. At time equals 0, what position is the man at? 8. At time 5, what position is the man at? 0. At time 15, what's the position? And at 17, 11. And you can connect these. We don't know exactly what the path is between those, but they connect in some way. And so there's a position versus time graph of that motion that takes into account our choices of the zeros and the positive direction. Let's do, so for part B, let's do the same thing, but this time we'll say our 0 position is at the house. Actually, no, erase that. Make that the mailbox. And our positive direction is toward the car. And our 0 time is 5 seconds before he starts walking. And I'm going to take the same picture and I'm going to use everything that is still good in this new example. Okay, so I have to erase some stuff. So okay, so notice that what I have here is still perfectly good with the new choices of 0 position and positive direction and 0 time. This is just describing what happens. The man still starts at the mailbox and goes to the car, back to the mailbox, back to the house, and it still has these elapsed times between. And all we're doing with the 0 time position, positive direction, is we're coming up with a way to represent this all numerically. Okay, but we don't have any control of what the man does. We're just watching it happen. So now we're going to say that the 0 is the mailbox. So this location is 0. The positive direction is toward the car. So this is positive. And 0 time is 5 seconds before he starts walking, which means that this location, when he starts walking at the mailbox, it's already timed 5 seconds. Okay, so now let's finish labeling these. the car is 8 meters in the positive direction from 0. So what's the number for the car? Yeah, positive 8. And now this is different. The house is 3 meters in the negative direction from the 0. So what's the numeric label at the house? Negative 3. And now the last thing we have to do is just add up the times. So 5 seconds later than 5 seconds. So this is at 10 seconds. 10 seconds later than 10 seconds. So this is 20 seconds. And 2 seconds later than 20 seconds. 22. And now I'll just read these. Read these off this picture. Here's the position. Here's the time. The times that we care about are going to be 5 seconds, 10 seconds, 20 seconds, and 22 seconds. And the positions we care about are going to be 0, -3, and +8. At time equals 5 seconds, what's the man's position? Yep. At time equals 10 seconds, what's the man's position? 8. At time equals 20 seconds, what's the position? 0. And then at 22 seconds, -3. And if you connect it all, it looks something like this. So what we got, if you compare that to the picture we did for part A, you got the graph shifted because of the change of your time equals 0. You got it shifted up and down because of your change in your position equals 0. And you also got the shape flipped because you changed the direction. Okay. Any questions? Okay, see you Thursday. So remember, there's a quiz on Thursday. So look over your notes and be sure you know how to do those problems because you might have to do one of the problems that's been assigned.